Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to continue going through Chapter 3.5 and look at some other prominent vector spaces. In our last video, we introduced these 9 other prominent vector spaces. And so what I would like to do today in this video is to continue looking at some of these examples. And let's start with M32. Let's show that M32 is a vector space. To show that M32 is a vector space, let's again write out what this might look like. M32 this is the space of 3 by 2 matrices, 3 rows, 2 columns, that might have elements A, B, C, D, E, F, such that A, B, dot, 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 F, all of our entries, are elements of the real numbers. Some typical vectors in our space. So even though we're talking about the vector space M32, we still refer to its components, the items in it, as vectors. So here's some typical vectors might look like 1, -2, 0, 1, -3, 2. This is what a vector in M32 might look like. However, if this is your vector, and let's call this vector x, the negative of x has to be in there. So we would also have to have -1, +2, 0, -1, +3, -2. Notice that this is still a 3 by 2 matrix. If any vector is in here, a scaled version of it has to be in here. So maybe we could look at the vector 2x. 2x would have to be the vector 2, -4, 0, 2, -6, 4. We would have to have a 0 vector in the matrix space. So here a 0 vector would look like a matrix of all zeros. And there would be lots of other matrices, of course, but this would be just a couple of them. And let's think about the required properties. The first one, the sum. And I would like to recall from what we know from previous work in Chapter 3 that the sum of 2 3 by 2 matrices would still be a 3 by 2 matrix. If you add a matrix plus another matrix, you still get a 3 by 2 matrix. Check. Unless you don't know how to add matrices, of course. The scalar multiplication property. And I always like to say K times some matrix is still going to be a 3 by 2 matrix. So a scalar of a 3 by 2 matrix is still a 3 by 2 matrix. Remember, these are the only two required properties, but we could also say a 0 matrix exists. And we could also say that the negative of a vector, a matrix, exists. I think these are enough for us to say that M32 is a vector space. But they're no longer vectors that point in R2. These are matrices of dimension 3 by 2. If you add any two 3 by 2 matrices, they stay a 3 by 2 matrix. A scalar of any 3 by 2 matrix is still a 3 by 2 matrix. There's a 0 3 by 2 matrix. There's a negative of every 3 by 2 matrix. It's a vector space. Okay. How about P2? It might be helpful to look back and recall what P2 meant. So P sub n is the space of all polynomials of degree less than or equal to n. So the degree is less than or equal to n. So here we're talking about P2. So P2 would be equal to the set of things that look like ax squared plus bx plus c, such that a, b, and c are elements of your real numbers. So with real coefficients. This is what P2 looks like. Typical elements of P2 could look like 2x cubed, not cubed, 2x squared, minus x plus 3. That's a P2 element. Remember, it could be degree 2 or less. So x squared plus 1 could be in there. Or x minus 3 could be in there. 4 is in there. 0 is a polynomial of degree less than or equal to 3. Okay, so there's lots of elements in P2. Not all of them are degree 2. They could be less than or equal to degree 2. And I want to show this is a vector space. So to show that this is a vector space, you'd want to look at the sum of two P2 elements. So maybe this might look something like A1 x squared plus maybe B1x plus C1, and add that to another P2 element. A2x squared plus B2x plus C2, where all the A, B's, and C could be real numbers. Of course, if we add two polynomials, we always add similar terms. So we would have A1 plus A2 times x squared. Here I'm just combining similar terms, so combining the x squared terms together. And now I'll combine the x terms together. And now we'll combine the c terms together, the constants. But notice that what you get back is still going to be an element of P2. It'll still be a polynomial of degree 2 or less. The scalar multiplication property. If you looked at some scaled version of an element of P2, and here you'd probably want to distribute your constant k to each term in your polynomial. So distribute k to each term. But notice that this is still going to be a P2 element. Not R2, P2. So we've showed that it will always satisfy scalar multiplication and addition. But again, I like showing others, like, is there a zero vector? And the zero vector would look like 0x squared plus 0x plus 0. This is your zero polynomial. This is an element of P2. Is there a negative vector? So for example, if I were to give you the polynomial 2x squared minus 3x plus 1, then you'd be able to say the negative would be negative 2x squared plus 3x minus 1. And the sum of these two vectors would equal 0. And this is an element of P2. Now again, all you're required to show with vector spaces is you always satisfy the closure properties. I just like talking and showing about these other ones because if you fail one of these properties, then you're not a vector space. So the closure properties are required. So P2, that's a vector space. Let's look at some differential equations. Here I'm asked to show that the solutions of the differential equation form a vector space or show what property it fails. So I want to show that they form these solutions. I want to show that the solutions form a vector space or show what property it fails. If I'm going to show that the solutions are a vector space, maybe we should first go look and see what the solutions look like. So let's first find the solutions. And I'm going to find the solutions, I think, using separation of variables. It seems like the easiest, most straightforward technique for this problem. So to do separation of variables, I'm going to rewrite y prime as dy dt, and I'll move the other terms to the right-hand side of the equation. Maybe we could divide by y, and then multiply to get the dt on the right-hand side. Now that we've separated our variables, you'll probably want to integrate each side with respect to the variable that's present. And this should seem familiar to us now. This would be the natural log of the absolute value of y equals right-hand side negative t squared is your antiderivative plus your arbitrary constant of integration. To solve for y, you'd raise each side with base e. Remember, all of this has to be an exponent on e. And maybe you use the property then that the exponent and the natural log cancel on the left. And on the right-hand side, let's write that as a product of two exponents. So e to the negative t squared times e to the c. Remember now that the e to the constant, if c is some constant here, then e to the c is still some constant. So maybe we can write this as the absolute value of y equals c e to the negative t squared. And then now remember that your constant c can absorb your absolute value. And so we get y equals c e to the negative t squared. This is your general solution. And so now again, we're being asked to show that the solutions form a vector space or show what property it fails. So now let's move on and let's show the properties. So here specifically, we want to show the closure properties. Or show that it fails one of these. So let's start first with the addition property. To show the addition property, we have to have two solutions. So let's let maybe y1 and y2 be two solutions to this differential equation. Of course, y1 and y2 will only differ by their constant. So maybe y1 will look like c1 e to the negative t squared for some constant c1. And y2 will look like c2 e to the negative t squared for some constant c2. But if we were going to add these together, maybe we could factor out your common factor of e to the negative t squared that's common in both of these solutions. And I think we would have c1 plus c2 times e to the negative t squared. But then I would probably say let's let c equal your sum of these two constants. And so we get c e to the negative t squared, which is still an element of our solution space. It still fits the general form of what our solutions look like. Check. Let's look at this scalar multiplication property. So here we want to show The scaled version of some solution is still a solution. So here we'd be looking at a scalar version of c1e to the negative t squared. Of course, we can reassociate these parentheses and call this k c1 times e to the negative t squared, or just call this c e to the negative t squared. But notice that this is still an element of our solution space. Check. Is there the presence of a zero vector? So here I'm asking, is y equals 0 a solution? So let's grab our differential equation, which was y prime plus 2ty equals 0. So let's plug in our proposed 0 solution. And we're asking, is 0 still part of our solution space? And so notice this is saying 0 does equal 0. Check. 0 is an element of our solution space. So putting this all together, I would like to be able to conclude that here the solutions of y prime plus 2ty equals 0 form a vector space. Okay. Let's look at another example. Here, I'd like to show that the solutions of y prime plus 2ty equals t form a vector space, or show what property it fails. And I'd like to have you work on this on your own for a moment. So if you could, please pause the video and look at the solutions of this differential equation, and then see if they verify the requirements that we need. So pause this video, do this on your own, and I will see you back here in a moment. Okay, let's see how you did. If we're going to be trying to show that the solutions form a vector space, let us first go find the solutions. Now, this is a linear differential equation. We could use the integrating factor method or separation of variables. I think for this example, I'd like to do separation of variables again, though. If you did another method, that's fine. So to use the separation of variables technique, I'm going to write this as dy dt equals, I'm going to move this 2ty to the right-hand side and write this as t minus 2ty. And to separate, I'm going to maybe factor out the common factor of t on the right-hand side. To write as 1 minus 2y. We can divide to get all the y's on the left. Multiply to get the dt on the right. And then choose to integrate each side with respect to the variable that's present. Now on the left-hand side, again, this is not the easiest integration, but I think it looks a lot like the integral of 1 over x dx, which we know is the natural log of the absolute value of x. So I'm going to make that guess that the antiderivative is the natural log of the absolute value of 1 minus 2y. And then imagine if my answer's right by checking my derivative. I'm going to erase this, but just to show my work, I'm going to say the derivative of natural log of anything is 1 over the anything times by the chain rule. The derivative of the anything is -2. When I'm comparing this to the original integrand that we had, I'm recognizing that that -2 shouldn't have been there. So it makes me think, but what if I had a multiplication by -1/2 that would have been in front? Then it would have canceled that -2 and I would have had the correct antiderivative. So I like this guess and check method for antiderivatives. I would have never shown this to a Calc 1 student, but I feel like we are ready for some of these shortcuts that we can make. Okay, the right-hand side, the antiderivative of t would be the 1/2 t squared plus some constant of integration. Okay, now let's solve for y. Let's multiply both sides by -2 to get natural log of the absolute value 1 minus 2y equals, when you multiply by -2, we'll get a -t squared. Now remember, multiplying everything by -2 here. -2 times this side, -2 times this one, and -2 times here. So here the -2 and the 1/2 will cancel. And here -2 times c, remember if c is some arbitrary constant, -2 times c is still a constant. I'd like to just call it a constant. Okay, now to get the y by itself, we'll exponentiate each side with base e. With the expectation that the left-hand side, the exponent and the natural log will cancel. And I'm going to write this right-hand side as a product of two exponentials. Let me rewrite this left-hand side a little bit better. Okay. Now remember, if c is some constant, then e to the c is still just some constant. So I'll write this as 1 minus 2y equals c e to the -t squared. Remember, the c can absorb the absolute value. Now subtract 1. And then we can divide everything by -2. To get y equals, now recall, if c is some constant, c divided by -2 is still some constant. So I'll write this as c e to the -t squared minus 1/2. This is the general solution to our differential equation. Now what we want to do is to show that the solutions will form a vector space, or show what property it fails. So now let's go show the required properties. So remember, we only have to show two properties, the addition and the scalar multiplication. So let's look at addition first. So let's grab two proposed solutions. Let's call them y1 and y2. Recall that y1 and y2 only differ by a constant c. That's our initial condition. That's going to be from our IVP we'd solve for c. So maybe y1 would look like some c1 e to the negative t squared plus 1/2. And maybe y2 would have a different constant. So let's call it c2 e to the negative t squared plus 1/2. And if we add these two individual solutions together, we'd probably combine similar terms. So let's combine the exponential terms. That'll have a common factor of e to the negative t squared. So maybe c1 plus c2 e to the negative t squared. And then if we combine our constant terms, the 1/2, then I get plus 1. And maybe in general, you could say that this is going to look like c e to the negative t squared plus 1. And I'm asking, will this still look like one of my general solutions? Will it still look like this? And what I'm noticing is the constant terms at the end. Here we had a minus 1/2. That's what our solutions always looked like. But when we add two solutions, we don't have the 1/2 at the end anymore. Now, technically, you might remember that this was going to be our transient solution because it goes to 0, and this was your steady state solutions. So these are going to have different steady state solutions. These are not the same. And so I want to say this is not part, or let's not say part, let's write it as this is not an element of the solution space. If this is not an element of the solution space, we're done. We don't have to check any more requirements. If you fail the closure property of addition, there's no reason to check any of the other properties. However, I like, again, emphasizing the 0 vector as a great one to check. So let's say, is the 0 vector present? So let's grab our original differential equation, the y prime minus 2ty equals t. And let's plug in our proposed 0 vector. So here it'd be 0 prime plus 2t times y equals 0. And we're asking, does y equals 0 satisfy this differential equation? And I think what we get here is 0 does not equal t. And so my conclusion with this would be y equals 0 is not part of the solution space. And maybe that would have been an easier one to check rather than going through the closure of addition property. However, in the end, I think what we want to know about this problem is that here, solutions of y prime plus 2ty equals t do not form a vector space. Okay, let's look at another example. And here again, we're being asked to show that the solutions of this differential equation form a vector space, or show what property it fails. And right away, I'm considering what our last problem faulted, is that 0 was not a solution. If we would have checked this first, we wouldn't have had to go through and solve this differential equation at all, because 0 was never going to be a solution. So with this one, I'm trying to learn from that right away. Is 0 a solution? So maybe just note here, is y equals 0 a solution? So we would be looking at 0 prime plus 0 squared and asking, does this equal 0? And I would be saying yes. So that was an easy one to check. But that is not all we have to check. We have to verify that the solutions in general form a vector space. So let's go find the solutions now. And I'm going to use separation of variables again. So I'm going to write this as dy dt equals, I'll move the y squared over to get negative y squared. And we can separate our variables dividing by y squared, multiply to get the dt on the right-hand side. Now, of course, I'm going to want to find the antiderivative, but I think it'll be easier if we rewrite this with a negative exponent. And let's find our antiderivatives. So here, the antiderivative of the left-hand side would be the opposite of the power rule. Let's add 1 to our exponent, divide by our new exponent. Right-hand side, the antiderivative would be t plus c. Getting rid of our negative exponent, maybe this looks like negative 1 over y equals t plus c. And I want to solve for y, so I'm going to multiply to get the y on the right-hand side and divide by the t plus c to get it on the left-hand side. And so I want to write my solution as y equals negative 1 over t plus c. And observe, this is what our general solution looks like. Now we know 0 is a solution already. We got that one down. But remember, that's not the property we're required to show. Here we have to show the closure properties. So let's look at the closure of vector addition. So we want to show that if I took some first solution y1, added it to a second solution y2, will the sum still look like one of our general solutions? Now remember, y1 and y2 are only going to differ by some constant that would depend on our initial value problem. That's how we found our c. So maybe y1 would look like -1 over t plus a first constant. And y2 would look like -1 over t plus some other constant. Call it c2. Now, if we were going to add these two fractions together, we would have to have common denominators. So maybe we would multiply this one by t plus c1 on the top and bottom, and this one by t plus c2 on the top and the bottom. But I think what we would get back would be, let's see, it would be -1 times t plus c2 minus 1 times t plus c1 all over our common denominator, which would be t plus c1 times the t plus c2. And I'll do a little bit of simplifying here. Maybe we could distribute these -1s into the parentheses and combine like terms. I think I'd get -2t minus c2 minus c1 all over our common denominator. And now I ask, does this look like one of our general solutions? Does this look like one of these guys? And I think the answer is no, or no way, which means that we failed the closure of addition. Our solutions to y prime plus y squared equals 0 do not form a vector space. So maybe we can now put down a summary of what these last three examples should do for us. Is, when do the solutions of a DE form a vector space? So we can say the solutions of a DE will form a vector space when the following two properties are held. One, the DE must be homogeneous. And that's how we're guaranteed to get the 0 vector in there. And two, the DE must be linear. As our last example showed, this differential equation y prime plus y squared is not linear. And that's what caused this to fail. You must be linear. Of course, this guarantees us the superposition principle. That the sum of two solutions is still a solution. So that's really what we are looking at, is that the superposition principle will hold. It means your differential equation must be linear. Okay, I'm going to stop this video here. I want to do one more set of examples, but I'm going to do that in the next video so that we can break these videos into smaller segments. I will see you in the next video, and I hope this is helpful.